This week, I'm going to do a little bit different on my recap for the week. I'm going to summarize 3 robotics talks that I attended, which were really interesting. And then I'm going to do also a discussion on a philosophy talk about intelligence and embodiment of intelligence, which I think fits well. And then I'm going to talk about the other events separately. The reason, first, it's in the with respect to time. I don't want this episode to be more than 20 minutes. And last week I had a 40-minute recap episode. And this is really also very important. So I think I can fill quite a bit of content with the robotics side of things. Now, we at Orange Capital Partners, we're invested in real world AI. So we obviously have a huge interest in robotics. And I would say my sabbatical at Stanford is primarily through the viewed through the lens of robotics. So what's going on there? What are the latest scientific developments, and what do we think can be commercialized, and where do we think Tesla and NVIDIA are large positions stand relative to the developments in AI? So that's kind of where we stand. That's why I think robotics is a very important part of the equation. So 3 talks and 1 philosophy talk. In the prelude, I just want to mention quickly the talks. So He Wang, Peking University, he is a roboticist there, and he talks about sim to real. He wants to solve the grasping problem, and he wants to create simulation data as much as he can, and then learn from there. I think there's some very interesting thoughts that I gathered in this talk. One is the enthusiasm that he has for Tesla, which I haven't been really, able to detect anywhere else at Stanford, in particular not in the, cars seminar, which was ridiculous when people talk about the future of transportation and how they sort of are paving the way for electric autonomous cars, and then not even mention Tesla. So clearly there's an academic almost repulse relative to Tesla. Not in China, not this He Wang. He was all over Tesla, basically trying to replicate what they're doing. I think the biggest takeaway for the week, in my opinion, is the necessity to bootstrap robotics. I had an episode about this yesterday, so I'm just going to mention it here again. This is really important. This is one of the biggest takeaways, the necessity to bootstrap robotics. So we have to find a way to get robots to do something useful at scale, and then learn from them, use their movements to build a foundation model of multisensory tokens that then can be used for more interesting upstream type of tasks, and go from there. So this is the key thesis, and Tesla's on the way to do that because they have a couple of things running for them. One is they have the mentality and the mindset of low-cost robotics. This is key. In order to scale up robotics, they have to be low cost of compute per watt, low cost of actuators, low cost of robots per se, because you can't have these things fall down all the time. I think the other interesting thing that I got from the He Wang talk was, what can robotics do for simulation? That's a very interesting question. I'm going to discuss this a little bit further. The next talk, Ding Zhao, he spoke about task-specific learning. I think the biggest takeaway I got from there was the need and the difficulty of adding learning to existing learning without having collapse, forgetting something that I think is just a real model problem. How do you create a model with weights and parameters that don't forget when you add new weights and new parameters, in other words, new tasks to it? Last talk I attended was Fei Miao, and she was talking about how to quantify uncertainty in computer vision in particular. She was also talking about multi-agent collaborative games that can be sort of played, or reinforcement learning applied to how multi-agents, how particularly autonomous multi-agents move. So this is she has a PhD in statistics and comp sci and electrical engineering, and her expertise is in the mathematical application of game theory. So she's kind of a 2023 version of, if you will, von Neumann. And what I thought interesting there is, like, when we talk about this reinforcement learning approaches towards multi-agent behavior in traffic, how do we deal with canonical sort of behavioral problems, such as the prisoner's dilemma, free riding, these types of things. How do we deal with that? And I didn't have a chance to talk to her about this. I'm kind of keeping my Q&A participation a little bit on the back burner because I don't want to be too aggressive in those seminars. They really aren't actually meant for people like me. So that's besides the point. Last thing I want to talk about is a lecture I attended at the East Asian Institute about Confucius, and that was interesting too because first I asked the question, okay, what does knowledge, what does humanities have to say about how we teach machines? And the person, I forgot the name of the person. He's an East Asia specialist in the philosophy department of the University of British Columbia. I'll put in the show notes his name. He actually said that the only way that machines will ever be able to think and have the kind of intelligence that humans have is if they're embodied. So you need embodiment, you need movement. Even there was discussion about Confucius and how he presents the odes, which are basically poems about life, about humans, about humanity, about how humans are, and they imply also movement like dance and music and probably even more than that. And I think you go back to ancient religions, back to yoga and the Hindu and the Buddhist religions, let's say in the East, they all embody movement. I mean, yoga is moving exercise, in a sense, also a prayer, if you will, not a prayer in a sort of traditional monotheistic sense, but you move your body, you let yourself go, you let your thoughts go, and you try to be whole with the fundamental forces of nature. In that conversation, actually, there was this interesting question raised, which is how do we compare Confucius with Lao Tzu and Taoism? And the idea here is that Confucius is all about rituals and rules, and Taoism, as propagated by Lao Tzu, is more just understand the essence, understand the fundamentals of human nature, and then um, learn from there and be simple and keep it short. And I think this is a real interesting conversation that propagates throughout AI now. Okay, do we explain everything? Do we explicitly train robots? First of all, do we need embodiment for intelligence? And then if we train embodied machines, do we train them in task specific? Do we explain to them what they need to do? Or do we have some sort of fundamental, almost like a fundamental um, law of nature that we can teach them, or a fundamental vector or vector space that once they learn that, they can move around. I mean, this is a really interesting conversation that I think really propagates throughout AI. So this is an Not Even Wrong podcast. It's November 11th, 2023. This is Grimdelco. For the year, we are up 88.3%. The market is up 14.8%. We're outperforming by 73.5%. So the first talk I want to talk about this week is by He Wang. He Wang is a researcher at the University of Peking, and he is in the business of trying to teach robots how to move, give them specific tasks. His motivation actually is, according to him, that the Chinese are investing a lot of money in robotics because they need somebody to take care of the old. So there is a real effort in having robots do household work, help you with opening the door, closing stuff, cleaning stuff, that kind of thing. I don't know why the Chinese are obsessed with that, but they are, and it's obviously an interesting problem. It is tangential to the humanoid robot problem that Tesla is trying to solve, and that's why it's so interesting to us. Now, what He Wang is doing, or what he presented in this particular paper, is the idea of sim to real through understanding depth and training a robot with millions and millions and millions of iterations in simulation of how to pick up stuff. And I mean, there's a couple of interesting questions that come up here. First, okay, can you do this brute force approach? You don't have physics, you don't have material sensing, you don't have multi-sensor sensing. All He Wang is doing is solve the problem of depth, understanding where is something and how far do I have to reach to grasp it. So that I thought it was interesting because a lot of the papers that I come across in archive and in presentations, they're trying to solve multi-sensor, there's touch, there's vision, there's all kinds of stuff. At the BARS conference, there was a paper presented that spoke about, how to grasp things in very difficult environments. And they said it's mainly vision, not so much touch. So we're sort of moving towards a world where robots will have more than just vision, but right now He Wang is fully on vision and dealing with the depth problem. Now, my question here is, isn't that already solved? And I think this is where I think Tesla comes in. This is one of the big revelations I had in this particular talk, which is that Tesla actually has solved for depth through their camera vision only, self-driving suite, and they can transfer learn that into the robots. This is a massive, massive plus. They can use that also in simulation. So I would have liked to ask him what he thinks of Tesla, but just given his presentation started with Tesla all over the place, Tesla is this, Tesla is that, Tesla is advanced, we have to do what they're doing, we have to have millions and millions and millions of hours of training. So he is definitely on that bandwagon. It made me think that that is something that the academic community per se is almost jealous about, that the Teslas of this world have the opportunity to solve the robotics problem and they don't. But that's besides the point. I don't want to talk about the academics too much. I'll have a special episode about this maybe towards Christmas or so when I sort of summarize my sabbatical, my first impressions, and my feeling about the world of academia. Let's get back to this paper. I think the other big takeaway I got from this paper, so takeaway number one is definitely Tesla's on the right track. Tesla has this ability to bootstrap itself, transfer learned depth into simulation or real world application for the human robot, and this is a huge, huge first step. Of course, there's a lot more to do. We need also better actuators. We need better sensing for geometry, other than geometry, like physics and sensing and material. So what He Wang is solving is geometry. So it's pure geometry. Okay, where is something? What's the shape? How do I grasp it? And then he applies this in the real world. So it's working well, and the robots are able to grasp things relatively well with very little mistake. We're still talking 78% accuracy, so they're not able to grasp everything. But the problem is this: can you grasp very unevenly shaped materials and things like bottles and balls and things? He's not solving the egg problem. That's something Tesla's showing off in the video. They're not solving that problem, but that's because that implies physics, that implies touch. This is just geometry. I think the other thing that made me think in this episode, in this presentation, was the concept of, okay, what can robotics do for sim? So first of all, should we invest more in sim? What exactly is simulation? What are the problems? I think simulation as a field should be part of robotics, and it's not right now. And I'm interested in exploring a little bit more what is actually going on with simulation. I'm going to attend some conferences there, in particular at the New York conference. If I go, I'm invited, but I'm not sure I can go. That's a different story. But if I go, I will definitely spend more time on sim. Just remember my conversation with Stendra Malik, where he said that he's most excited about sim. The next talk was Ding Zhao from Carnegie Mellon. He is talking about task-specific learning. I think the specific problem that he spoke about is continuous learning. So this is the problem. The problem is that you teach a robot how to pick up a bottle. Now, how do you teach the robot how to pour water from the bottle in a glass? That's an additional task that can be learned by. There's a couple of problems. One is the sort of statistical problem of, okay, we have new data now coming in, how to pour a bottle, which is a completely different data set than grasping a bottle. How do we combine those, and how do we teach how do we focus on the data that is task specific? So how do we take a data set and get rid of all the data that is not task specific. This is sort of training slash cost slash memory type issue. We don't have all the data all the time. We only have task specific data. This is something that I believe Tesla has been talking about for years now. They have millions and millions of miles. How can they focus on tasks and get rid of all the miles driven that are not necessary for the particular task? This is something that people like Ding Zhao are working on the analytic academic side, and that's definitely something that transfers back to companies like Tesla. The idea is you look at sort of the Gaussian distribution of the data set. Let's say if I drive on a highway, there's a certain distribution. We have the lanes, I have the front, side, and things like that. And then I want to have a new data set where I learn how to take an exit. Well, that's a very specific instead. I have to move my sort of distribution from left to right, let's say, in the sense that I have to focus down the data that is particularly related to the turn and get rid of the data that I don't need. And that's something that also has statistical implications in the sense that, okay, how do I actually manage my data set so I can dynamically adjust the amount of data that is being used for training and make it task specific. This is a problem that I'm not particularly familiar with how to solve it technically, but it's definitely a problem. And that's what Ding Zhao was talking about. He was talking about the cost of training, for example, and inference, by the way, when you have task specific problems where you basically save yourself a lot of space with data that is not needed for the task, but you have to make sure you don't forget the other stuff that you learned before. So if you know how to drive straight, you now learn how to take an exit or how to change a lane. But how do you make sure you don't forget how to keep the lane? That's a problem that has been relatively well solved, but it's still an open problem. The last talk I want to, the next talk I want to talk about is Fei Miao. Now, she was really interesting. This is a woman. She's a University of Connecticut, and she talks about the quantification of uncertainty. That is her thing. She's a statistics person. Her major is statistics and PhD. All of her academic work has been in sort of the mathematical concepts of data analysis, statistics, and the quantification of uncertainty is a real big problem in statistics. And it goes back to things like maximum likelihood, which is okay if I have a certain data that comes from my I sample, like I have a certain model, it gives me certain data, and now I sample the data, and what's the likelihood that the data I sampled actually comes from the real, that it comes from the actual real world, that it comes from the model that the real world really represents. So it's those types of concepts that I'm personally not super familiar with. Likelihood functions in general, where you have, okay, what's the likelihood that this data set belongs to the real world? That you're really grasping what is going on in the real world. This is really what she's trying to solve here, right? I have a certain observation that I generate synthetically. What's the likelihood that that observation actually represents the real distribution of the data? That's fundamentally the question. I've come across this in my economic work when I did my master's, and it's really very tedious statistical work, but it's important. It shows that a lot of people say if you want to get into, let's say, reinforcement learning, get a math degree, get a statistics degree. I absolutely agree with it. It's not the most glorifying thing to do, but once you have that backbone, you can then start solving real problems, such as, for example, multi-agent reinforcement learning, where you have what Fei Miao did. She also added communication to the equation. So she asked herself, okay, if I have multi-agents that have communication, how can I improve learning? The concept of learning itself, the concept of how to quantify uncertainty actually is a very interesting concept because you can define learning as reducing uncertainty, and there's a certain fundamental uncertainty, which is sort of and there's two expressions of uncertainty. One is called the epistemic uncertainty, and the other is that something with A, I forgot the word. What that means is that you can have two types of uncertainties. Okay, one is that your model is not really well capturing what the actual world looks like. That's the kind of uncertainty where the model system I put enough, it doesn't have, let's say, it doesn't have, that's sort of the edge cases when you have, a truck carrying a red light on the back in the load, and then the model just can't capture it. It has never learned that. And then there's the other one, the one that starts with A, which is that is a fundamental uncertainty which comes from you just don't see well. For example, you don't have the ability, even though your model is good, the data that comes in is not enough. This goes back to actually the sort of compressed data analysis problem that I attended a talk the day before about this gentleman from Berkeley who thinks about these things. Okay, how can I represent something with very, very little data input? I'm going to talk about this in a separate episode. I don't want to mix this up, but you can see how all these fields tie together. This is really what's so beautiful about this sabbatical. You can connect the dots. It helps you connect the dots. You see where science is. You see where science is also what kind of surfaces science is scratching, and this problem of having uncertainty in general, uncertainty in let's say in computer vision can be solved by first we have to understand what is uncertainty, and then second we can try to reduce it. We can do that with machine learning, and we can also do that with maybe some statistical tricks. And I thought that was really interesting. So lastly, I want to talk about. Sorry, just to finish Fei Miao, I think also what her talk sort of inspired me to do is think about the multi-agent problem. I think the multi-agent problem is a traditional game theory problem, and the traditional game theory problems, there's some canonical problems like free rider, and for example, prisoner's dilemma. So I was wondering, how does she deal with that? I didn't ask her that question, but I was just wondering to get a better sense for sort of attacking a multi-agent traffic problem from a game theoretic reinforcement learning type perspective is a really, really interesting problem, because you have all the reinforcement learning issues actually even amplified. For example, how do I focus on policy versus reward? What kind of reward function do I use? These are all really interesting problems. I'm going to discuss them more definitely in episodes going forward, particularly during the course that I'm taking with Sergey Levin, the reinforcement learning course that Berkeley is offering in the fall quarter. So those are very interesting problems. I think Fei Miao is on a very interesting path here of understanding multi-agent behavior, of quantifying uncertainty, quantifying what is good behavior, what is bad behavior. All of those types of questions are, for example, you have a sort of a global reward function, a global policy, you have individual policies. How do you deal with that? Those are really, really interesting questions. Finally, I want to talk about the philosophy talk I attended at the East Asian Society, and this was about Confucius. And I think there, really the question of can we have intelligence without embodiment came up. It actually came up in philosophy, and I find that so fascinating. And our thesis on capital is no, we need embodiment. That's why we're invested in robots and real world applications, because that's how intelligence evolved in nature. And that's also what somebody like Confucius would say. I think the interesting thing about this talk with Confucius is also the difference between Confucius and Laozi. Laozi is about sort of finding the eigenvectors of nature and then following them, being concise, being, parsimonious about, okay, what matters, and then follow that, versus Confucius has all these rules, all these rituals, and then it's more like explicitly programming what one should be doing. So those are the two big, I would say, paths that humans can go. On the one hand, we decide, okay, what is and what isn't on every little detail hierarchically, or we have this fundamental laws of nature, if you will, or I don't know what the exact word is in Taoism, but it's like, okay, this is the essence of things. Let's learn that and then go from there. Summarize this week, very productive. 3 talks in robotics and 1 talk in philosophy. I'm going to talk about other events I attended. Those are just 4 events I want to talk about in this episode. One, He Wang talking about sim to real in terms of grasping, solving geometry problems. Second, Ding Zhao talking about the sort of task-specific learning. Fei Miao talking about quantifying uncertainty, multi-agent reinforcement learning, and then philosophy talk about the embodiment of intelligence. I think the big takeaways from these talks: number one, Tesla is bootstrapping itself on the robotics side through transfer learning and building low-cost robots. This is incredibly important for the robotics community as a whole. And second, what can robots do for sim? So it's not just sim to robot, but also what can robots do for sim? Third, how does multi-agent reinforcement learning deal with sort of the canonical game theory problems? How do we quantify uncertainty? Can we define learning as reducing uncertainty? Fourth, continuous learning is a fundamental task that I think needs to be solved from different perspectives, also the low-cost perspective. And I think finally also, why is the academic community not embracing what Tesla is doing more?